So our regressions so far have looked like this. We've had a dependent variable, and we've had our independent variable. And the first case we looked at is when we had a dependent variable that was continuous and a single independent variable that was continuous, or multiple continuous independent variables. Then when we started looking at dummy variables, we still had a continuous dependent variable, but this time now we were able to bring in a categorical independent variable. Okay, and so these were dummies, and so they were encoded as 0 or 1. Okay, but there are also cases where we would want to be able to predict a dependent variable that is categorical. And we're going to confine ourselves to just looking at 0, 1 for now. And then any configuration of independent variables. So any combination of continuous or categorical variables can be used to predict a categorical dependent variable. Now, there are lots of cases where we might want to do this. And so, for example, if we want to be able to predict whether somebody will buy something, right? So we have these two cases where we have buy or not buy. Okay, so we can encode the buy as 1 and the not as 0. Okay, or if we're doing like a human resources thing, we want to determine, to try to see what factors cause people to quit or not. Okay, so 1 would be quit and 0 would be not quit. If we are, sending out a promotion and we want to know if somebody is likely to respond to something, then we're interested in respond or not respond. And once again, we've got this case where we want to predict a 1 or a 0. Okay, well, why not just do what we've done before and just say we've got our usual regression line here, and we've got our x. We'll just, to keep it simple, we'll just pretend we only have one x variable, and this will be our y, right? And so we've only got two possible values, right? It's going to be a 0 or it's going to be a 1. Okay, so all right, well, let's say we've got so we treat the 0, 1 as a continuous independent variable, and we do our regression as before. So we'll just do, y. We'll have a model like this. Y is equal to some intercept plus some slope times x. Okay, and we wind up with a line like this. Okay, so a line, stretches infinity in, each direction. So, okay, so what's the problem with this? Well, if we look at here, I mean, this is good in a way, right? Because we can actually, if we put in our x variable and it's between here and here, that's just fantastic. So we'll call this x1 and x2. Okay, and so if we put in, let's say here, then this would give us back something close to 0, right? So this would say this is maybe 0.1, and if we put in an x here, this would give us back maybe a 0.5, and this would give us back maybe a 0.9. Okay, and so if we look at this, these are very nice, right? Because these can be interpreted as probabilities. So we could say, okay, well, the probability that y is equal to 1, given x, okay, is going to be equal to one of these. So, 0.1, for example. Okay, so if we just treat this binary variable as continuous, then between here, we have something that would suffice, and it would give us, an approximate probability. So this is like a probability, okay? But the truth is, this is not really, there's several problems with this, both theoretical and mathematical. Just to deal with the mathematical ones first. The problem with this linear function here is that it's not constrained to be between 0 and 1. That we could wind up, let's say we have x here. If we put in this, let's call this, x3, and we put in x3 in here, and it gives us, what would this be? So the y would be, say, negative 1.5. So how do we interpret that? What do we do with a number like that? Or likewise, let's say if we have a number out here, and this is x4, then, this might output something like 1.6. How do we interpret that? We might just say, okay, well, let's just chop it off. Let's just, let's just say any x down here, just say it's 0, and any x up here, just say it's 1. Okay, so really what we want is this kind of a shape here. Okay. So, well, this is fine, but really, we don't want to treat probability as actually being 0, right? Because we don't have any kind of guarantee. We want to know maybe something close to 0, but a function that outputs 0 for a lot of values is missing a lot of nuance. Okay, because x could take on any value in here, and it's still just spitting out 0. And likewise up here, it's just spitting out 1. So, for both the theoretical reason that we don't really want a lot of zeros, and we don't really want a lot of ones, we want to kind of have something that's smooth, rather than this abrupt, but kind of, reflects the reality of how this variable affects this outcome. And we also want it to be what's called asymptotic. So you probably saw asymptotes in, like in high school algebra. So the idea is that we want to have something that would, between these values, let's see if I can draw it here, we would rather have something that doesn't actually get to 0, but, gets infinitely close to 0, and then kind of is a smooth upward thing like this, and then gets asymptotically close to 1, but never actually gets to 1. Okay, so we would rather have this kind of smooth function here that would give us, that should not go over the 1 line. Okay, so this is what we want. Just to give you a little nicer picture of it here. So this is the line that I drew. So this would be just the linear model. If we just put in this, we treated the outcome as just a continuous variable, we would get this line. And what the desired function would be this smooth thing here. Okay, so what we want to do then is to start with this, but then pass it through something that will make it look like this. And it turns out that there is a function that will do that. There's a function that will take anything from negative infinity all the way up to positive infinity and will give you this kind of smooth S shape. Okay, so if we had that function, then we would be able to get back a nice probability, right? Because we don't just want zeros and ones. What we want is, what is the probability that somebody will buy something? What is the probability that somebody will respond to a promotion? Okay, and then you can, make decisions like, okay, well, if this probability is greater than 0.6, then go ahead and send the promotional flyer. If not, then don't waste your money. Okay. So it turns out that there is a function that makes this transformation, and it's got kind of a fancy name, and it is the Logit function. Okay, and you don't worry about how this originated. I'm going to show you why it looks like this shape in a minute. But we've got this function where if you take something, if you take e to some power and then divide it by 1 plus e to that power, this function looks like this. Okay, so if we can take the output of this linear, so if we can find some linear equation that we can, and then pop it into here as this x, this will, give us our desired properties of it being between 0 and 1, it being smooth, and it being asymptotic. Okay, so let me just show you what this function looks like across a certain range. Okay, so I've put that function, so e to the x over 1 plus e to the x, and here in Mathematica, and I'm just telling it to plot this function ranging everywhere from -5 to +5. Okay, and so here's what it does. So it crosses this y-axis here, and it stretches to -infinity, never touches the 0, and then it stretches to +infinity, never touches the 0. And I can send this out further, show me what it looks like from -50 to +50. And again, we see, so it's sharper here, but it's leveling off, as it approaches y equals 0, and y equals 1, and then down here, as we approach -infinity, it goes to 0. Okay, so we've got this Logit function. So what we're going to do is we're going to ask our software to do a regression, but then do it so that what you're actually doing is coming up with these estimates such that when I apply this through here, I will get back a probability. I'll get back a function that looks like this. And this is called, because of this Logit function, this is called logistic regression. Okay, now this is one of the more intricate forms of regression. There are lots of subtleties that go along with this. In fact, honestly, it took me a while to get my head around all of the different pieces of this myself. But I'm gonna show you a bunch of little gotchas that are involved in this, and then at the end tell you, okay, what is it that you really need to know so you can concentrate on that. But Excel out of the box and Excel with the analysis tool pack that we added does not actually have any way to do logistic regression. So we have to put in another add-in, and I'm going to give you a reference for that. So there's this great site which is called Real Statistics, and they make an Excel add-in that includes a bunch more functions, and they're at this address. If you Google Real Statistics Excel add-in, that'll be the first hit. But what you do is you download it, and then once you've downloaded it, you put it into some place where it makes sense and where you want to keep it. Then you come to Options and Add-ins, and then you'll come down here to Excel Add-ins and click on Go. And so here it is. I have already installed it, but you won't see this Real Stats option at first. You'll have to go and browse, and you'll browse to the file that you downloaded from that website. But then once you have it and you've enabled it by clicking there, you're going to have this Add-ins tab. Okay, and under this Add-ins tab, you're going to have a Real Statistics button, and this will have a Data Analysis Tools option. Okay, so we're going to use that to do the logistic regression, and I'm just going to take the output and then show you how to interpret it. Okay, so we have a situation here. Again, so the key here with logistic regression is we have a 0-1 dependent variable, and we want to be able to predict zeros and ones given a set of input uh, independent variables. Okay, and that's what we want to do here. So our case is we've got a set of customers here. Let's say these are corporate clients, and we've got customer IDs, and we've got the number of times that they have that we have called them, that we have contacted them, and we've got a churn code, which is 0 or 1. Okay, so churn refers to when a customer no longer uses your service. So churn is when you lose a customer, basically. So we've got here we've got 15 customers who have churned and 15 who have not. And what we would like to do is to see whether this number of calls has a significant effect on the churn. Okay, so you see why this is a logistic regression case. So we're trying to predict 0, 1 given a continuous, although discrete, independent variable. Okay, so the way we'll do this, using the real statistics add-in. So we'll come to add-ins and go ahead and launch this. Okay, so you notice you get something real similar to the data analysis tool pack. You'll see a whole bunch of menu options here. Many of these will be familiar to you now, but you'll see that there's actually, there's even more in here than we had before in the other one. But we're going to look at the regression REG tab, and you'll see that right down here we've got binary, logistic, and probit regression. Now don't worry about what probit is. It's similar to the Logit function, but we're just going to do logistic. So we'll select that and click OK. Now the input range, you have to make sure that your data is arranged in this way for this particular add-in. See, it lets you select it, but it insists that you have your dependent variable on the right, as I do here. Okay. All right. Now I'm going to leave the rest of this the same, except I want to put the output rather in a new worksheet. Okay, so I'm just going to go ahead and click OK, and I'll close this. Okay, now there's a lot here, but I'm gonna walk you through the pieces that you'll need. So a lot of this has to do with how the algorithm under the covers figured out what the coefficients were. But for our purposes, we really just want to know what are the coefficients and how do we interpret them. So if you look down here, we've got our intercept, just like we had before, okay? And we've got this column here, coefficient beta, okay? So, and we've got our calls variable, and we've got its coefficient, okay? Okay, so this is the piece that we are interested in. And once again, we have, slightly different, we're not using a t distribution for the hypothesis test. We've got something called a walled here. But notice that we do have coefficients and standard errors as before. And we've got p-values as before. And what we can see from this p-value here is that the number of calls does in fact have a significant effect on whether or not a customer churns. Okay, so now, so where do we go from here? How do we use this to be able to predict something? Okay, well, what we want to do is to have some kind of probability. Okay, we want to be able to, now that we've got these coefficients, how do we actually put them together to output some probability given a certain number of calls? Okay, so let's take a look at a couple of functions here. Okay, so here we have our this is our logistic function. There's that S shape that we expect. The example here is the probability of passing an exam. Okay, and this is the independent variable is the number of hours you spend studying. Okay, so you can see the effect here that as your number of hours studying goes up, you have this notion of diminishing returns here, right? Okay, so that's why you want that smooth thing. And so if you have a small number, you've got these increasing returns to your effort here, but then it levels off. Okay, so this is a really good and relatable, I think, example for how to use the logistic regression. Okay, but remember that so what we're getting at is a probability. Okay, so the probability that our dependent variable is 1, given a certain x variable. Okay, and what we're going to do is take this linear estimate and then pass it through. Remember, this is just the Logit function, Logit. And so remember, that's just e to the x over 1 plus e to the x. Okay, and this exp is just Excel's way of it's Excel's function for e. Okay, so basically what we need to do is to take the output of the linear estimate and then apply this function, and this gives us back a probability. Okay, now I put down here something else because if you do some algebra, you can you like take e to both sides and simplify. You wind up seeing that the linear function is actually this thing, which is called the log odds. So one way you can interpret the coefficients is this is the change in log odds due to a 1 unit increase in the value of this variable. But the change in log odds is not really something that's very understandable. So you tell somebody, okay, well, this is the impact, this is the change in log odds, given 1 unit increase in x1. Okay, but that's not really very understandable. So we've got this logarithm here, and it's hard to know what effect that has on it. And we've got these probabilities embedded in here, and this odds, the reason it's log odds, this is odds. So if you have a probability over 1 minus the probability, this is referred, on the horse track as the odds. Okay, so for example, if you have a horse and you're told that its odds are 4 to 1. Okay, let's just say it's 4 to 1 for. Usually you express it as against, but it's 4 to 1 for it winning. Okay, so what this means is that you can express this as its odds are 4 to 1, which means that 4 out of the 5 races it wins, and 1 out of the 5 races it loses. So what this is, so the probability of its winning is 4 out of 5. This is 4 out of 5 divided by 1 minus 4 out of 5, which is that 1/5 there. Okay, so this is where odds comes into it, and this whole thing over here is called the log odds. So you can just say, well, these coefficients represent the change in log odds for a 1 unit increase in x, but that's not really very understandable. What we want to do is to try to get at what these probabilities are, okay, given certain x's. Okay, and I'll show you how to do that. So what we have to do is just take the estimates and then pass them through this. So we'll do that manually. Okay, so I'm going to make a little chart down here. Let me zoom in a bit here. Okay. All right, so we've got, I'm going to put calls here, and I'm going to put the what's called the linear prediction here using those. So I'm just going to be applying the line to these, and then I'm going to put the probability here, and well, we'll start with that. Okay, so linear prediction. So let's say we're gonna go everywhere from 0 to 20 to 40, 60 calls, 80 calls, 100 calls. Okay, and I want to know, okay, given this number of calls, what would the linear prediction be, and then what would the probability of churn be? Okay, so the linear prediction is just going to be this line. Okay, so that's going to be equal to the intercept plus the number of calls, which is here, right, times the coefficient for calls. Okay, and I want to go back and I want to make B28 an absolute reference, and I want to make B29 an absolute reference too, so that I can copy down. Okay, all right, so what do we have here? Okay, these obviously are not probabilities. Okay, all this is if we go back to the slide here, this is this line. Okay, so this is beta plus beta times x. We've got this line. So this is why we have values less than 0 and greater than 1. Okay, so it's not a probability yet. Okay, so you come back here. Okay, so how do we convert it to a probability? Well, we pass it through that Logit function. Okay, so that's just going to be exp to that linear prediction divided by 1 plus exp to that linear prediction. Okay, all right, now this looks like a probability. Okay, and we'll go ahead and copy it down. Okay, sorry, that should be 100. Okay, all right, so let's take a look at what this is telling us. So this is the probability of churn. Probability of churn, which means probability of the customer leaving. Okay, given the number of calls that I guess these are maybe service calls that they've had to make, the more they have called, the more likely they are to leave. Okay, and so we see that if there were no calls, the probability of churn was 0.19. Okay, as we went up to 20 calls, the probability was 0.4, and when we go to 40, we've jumped up to 0.7, and then as you see, once we were up to 100 calls, then we're getting very close to 1. It never gets to 1, but it gets very close to 1, 0.99. Okay, so now let's take a look at we can see that the jumps are not of all uniform size. Okay, so what I'm going to do is I'm going to put a column here and then say what the difference is. Okay, so I'm going to say, okay, how much did the probability change from the previous time? So I'm going to say, give me this minus this. Okay, so we see that the probability went up. Between 0 and 20 calls, the probability went up by 0.25. Okay, and I'll just copy this down. Okay, so you see that that as we get above 60, we get smaller and smaller increases in the probability. Okay, now if I were to just to do a really rough line chart of this, actually let me do a to kind of emphasize this, I'm gonna do a line chart of the probabilities. Okay, we'll do a line chart of this. Okay. So what this means then, so this is 0 calls and this is up to 100 calls, is the probability of churning does go up as the number of calls goes up, but it's following this shape. So the difference between let's see, this would be 20 and 40 calls, is larger than the difference between 40 and 60 calls, which is larger than the difference between 60 and 80 calls. Okay, I'm gonna go ahead and add some more values in here that may not make sense at first, but let me just get this chart out of the way here. Okay, so let's say we'll do, okay, we'll insert a row here, and let's go down to -20, okay, and we'll go up to +120. Okay, so these are already filled in, that's nice, so we'll copy this down here. Okay, let me see, can I copy the linear prediction? Well, yes, okay, and copy the probability. Okay, and copy this also. Okay, so I'm going to go ahead and chart these probabilities again. Okay, so notice this is starting to look very much like that S shape that we were talking about. Okay, so remember that what we have here on the y-axis is the probability of churn, and what we have on the x-axis is the number of calls. So if, when we were interpreting the coefficients for linear regression, we were able to say, okay, for a 1 unit increase in x, we can expect this amount of change in the dependent variable. Now notice why we can't do that here, because the change from 0 to 20 was not the same as the change from 20 to 40. Okay, so we can't interpret the coefficients the same way as we interpreted them for linear regression, okay, because it changes. Okay, so it gets faster, so it makes a big difference to go from, so the biggest difference here was from 20 to 40, which is this jump. Okay, so going from 20 to 40 calls made a big difference, whereas going from 80 to 100 made only a small amount of difference. Okay, so but the key there is that because of this S shape, we don't really have a very easy way to predict, to interpret the coefficient as saying, okay, well, in a 1 unit increase in this results in this unit increase in that, because we need to know what value are we talking about. So one thing, one way you might interpret these coefficients is just use what's called the margin, okay, or the marginal effect. Okay, and so because the effect of an additional call varies according to where we are, we might just say, okay, well, we'll use at the mean. Okay, so let's go find the mean of the calls and the number of calls. So we'll put the average here. So the average number of calls is 30. Okay. All right, so what's the marginal effect? So that would mean going from 30 to 31. Let's find out what that is. So we're going to go from 30 to 31. Okay, so again, our linear prediction is going to come straight from these coefficients right here. So we'll do is equal to this coefficient plus 30 times this. Okay, and got to make that absolute, and got to make that absolute. Okay, Okay, so this is the linear prediction at 30 calls, and this is the linear prediction at 31. Okay, now we have to convert it to that probability, okay, which we did by doing exp to that divided by 1 plus exp of that. Okay. Okay, so the probability went from 0.58 to 0.59, and so that marginal effect then we can just say is going to be equal to this minus this, okay, is 0.01. Okay, so one way to interpret the coefficients of the logistic regression is to just say that at the mean is 30, and one more call than that results in a 0.01 increase in the probability of churn. Okay. All right. So there's a lot of stuff involved there. Logistic regression, as I said, is kind of intricate and tricky. But what is it that you need to know? Okay. So in essence, logistic regression is appropriate when your outcome variable is binary. That is, if you're trying to predict a yes, no, a buy, or a not buy, and so you want to have some function that will give you a probability, and then you can do what you like with that probability. You can just say, okay, well, I'm going to establish my personal business cutoff is I'm only interested in a probability of greater than 0.6. Okay, but you do need to be able to have something that gives you a probability. Okay, now, so the coefficients, so when you do that logistic regression, the coefficients are actually giving you the betas of the linear prediction, and you have to pass that through the Logit function to give the probability. Okay, so you take this linear prediction, and then you pass it through, let's say this is, so we have to do e to this divided by 1 plus e to this. Okay, and so that gives you the probability that y is going to equal 1. Okay, so the coefficients cannot be interpreted the same way as for linear regression. Okay, so one really rough way that you can use logistic regression is just say, okay, well, we want to understand what effect this factor has on whether they churn or not. And if you look at your coefficients and you see that it's positive, you say, okay, well, this means that an increase in this increases the probability of a 1. Okay. But if you have a negative coefficient, that decreases the probability that it's a 1. Okay. And finally, exactly how large the effect is will vary according to the magnitude of the independent variable. Okay. So, and then to make matters worse, even in the case of multiple regression, it also affects on the magnet. It also is affected by the magnitudes of the other variables. Okay, but roughly, it's just important to know that this will give you a probability, and that the coefficients cannot be interpreted the way linear ones are. But in a rough way, you can just say, well, positive means it affects it positively, negative means it affects it negatively, and that's going to vary according to where you are. And the mean is a good one to use. Okay.